Hello, students. In this video, we are going to talk about autonomous differential equations, and we're going to see a lot of pictures, so this will be a fun lesson. Let's see. If you recall, the last video we talked about separable differential equations, and we solved both of these. Y prime is ky. This differential equation gave us exponential growth, exponential decay, and then the second one, y prime is minus 0.1 y plus 4. This came from a word problem about medication in the bloodstream after X hours. And we also solved this using separation of variables. Both of these are examples of what's called an autonomous differential equation. So let's write down the definition. An autonomous differential equation has the form dy dx, the rate of change of y with respect to x is some function of y. You notice both of these have this form. The right-hand side, we do not see x's in it. Okay, great. Now here are three more examples of autonomous differential equations, which we will look at in this video. Maybe I'll just make the remark here. The capital F of y is y squared plus y minus 2 for the first example, the capital F of y. So we can match it to the definition. We see it. It's y squared minus y cubed. For the second example, and this third one, the capital F of y is y natural log y minus y minus natural log y plus 1. Now I want to make an observation here. You see we have function of y, function of y, function of y. But anytime y0 satisfies f of y0 equals 0, so y0 is some number here, in particular here, y0, well, it could be 0 or it could be 1, for example. We will come back to this problem. But anytime this number y0 satisfies f of y0 is 0, the constant function y equals y0 is a solution to dy dx equals f of y. Because what do constants have? Well, constants, y equals a constant. The rate of change of y with respect to x is 0. And that would precisely hold for a number y0 like this. So this leads to this definition. An equilibrium point is a constant solution y equals y0 with capital F of y0 equals 0. These are constant solutions of the differential equation. All right, now in this video, except for finding equilibrium points, we will not typically be explicitly solving autonomous differential equations. Instead, we will explore these solutions qualitatively. And let's start with the definition. An equilibrium point, y equals y0, is stable provided, well, all nearby solutions approach this number y0 as x increases. I'll put that in parentheses. We always read a graph left to right, x increasing. This is a stable equilibrium point. An equilibrium point is unstable, okay, provided all nearby solutions move away from y0. And as x increases, semi-stable, well, the easiest way to think about it is it's not stable and it's not unstable. So it says, well, it's the third possibility. Some nearby solutions approach y0 and some move away from y0. Let me take you back to this example from the last video, we use separation of variables to solve. Very nice. This y, as I mentioned at the start, it gave us the amount of medication in the bloodstream after X hours. So let's just solve for the equilibrium solutions here, and we can figure out stable, unstable, or semi-stable. So I'm going to factor out the minus 0.1, just as we did to solve. Makes it a little bit easier to look at. And then we have y minus 40. This capital F of y is here. I will box it in pink. We can see the equilibrium point here. There's just one. We get that y equals 40. Now, how do you figure out if it's stable or unstable? Well, we can draw an axis. I will make it vertical because it's y values, but it's an axis. Here's 40. We could pick a value less than 40, pick a value bigger than 40, and test the sign of the first derivative. So let's pick, say, 30, it's fine, and pick, say, 50, it's fine. Now, what do we get? At 30, we have 30 minus 40, negative, and then we have this minus 0.1 in front, negative. Two negatives makes a positive. So here we have a plus. And then 50 minus 40 is positive, multiplied by the negative in front, this is negative. So what this says is, we have this equilibrium solution, which is here at 40. Solutions above 40 are decreasing, and solutions below 40 are increasing. Y prime is positive, increasing. Y prime is negative, decreasing, like this. And so you see, this is a stable equilibrium point. Here's an example. Find all equilibrium points of this autonomous differential equation and determine their stability. And we will also look at a picture here. So first thing we can do, we can factor. We have quadratic, it's y minus something and y plus something. Now let's figure it out. We need to multiply to -2 and add to +1. So the 2 will go here and the 1 goes here. We see our equilibrium points. We have y is 1. We have y is -2. Wonderful. Now let's make our number line. We have -2 and 1, and we can pick a point here, here, and here. This is very much like when we were doing intervals of increasing, decreasing early in the semester. So let's take, say, -3. Let's take 0, and let's take 2. We need to test the sign of the first derivative. -3. Y minus 1 is negative. Y plus 2, negative. So this becomes positive. At y equals 0, we have -1 times 2. Maybe I'll write this. It's a negative and a positive. This is negative. Finally, at +2, I have 2 minus 1, 2 plus 2. So I have a positive and a positive. This is positive. So positive, negative, positive. Then here is equilibrium point, equilibrium point. So what's happening here? Solutions in here are decreasing. Solutions down here are increasing, and solutions up here are increasing. Solutions here decreasing. So you see, y equals 1, unstable. Y equals -2, stable. What we are looking at, while the green gives 4 different solutions to this autonomous differential equation, dy dx is y squared plus y minus 2. We calculated y equals 1 was unstable equilibrium point, and y equals -2 was a stable equilibrium point. And we can see this. So if I move around these points, we are getting different solutions. Well, I should also say these black dashes are giving you slopes at each point. Okay, so if I move these around, you see this line y equals 1, the solutions are moving away. Nearby solutions are moving away from that equilibrium point, and this y equals -2, that all nearby solutions are approaching this equilibrium point. We can certainly change these solutions. This is the beauty of this app. So I like looking at these pictures as we discuss autonomous differential equations and their solutions. I have just included a screenshot from the GeoGebra so we can see our equilibrium points were here and here. And just like we calculated and just discussed, y equals 1, unstable, y equals -2, stable. Let's move on to the next example. dy dx is y squared minus y cubed. Maybe I'll just write this here. We can factor out a y squared, and then we have 1 minus y. So you see the equilibrium points, y equals 0 and y equals 1. Now, make our number line. We will determine their stability, 0 and 1, and then we can pick a point and figure out the sign of the first derivative. So say we take -1, say we take 1/2, and say we take 2. Well, here, this part is always positive. It's a squared. So for all of these, the first term is always positive. 1 minus 2 is negative. So this gives a negative first derivative. 1 minus 1/2 is positive, so this gives a positive first derivative, and 1 plus 1 is positive, so we have a positive first derivative. Okay, let's highlight here, negative, positive, positive. It says decreasing, increasing, increasing, and equilibrium point, equilibrium point. And so it's going to go something like this. We have increasing, we have increasing, we have increasing. Up here we have decreasing. Now, y equals 1 is the easier one. We see this is stable. But you notice what's happening here with y equals 0. On one side, the solutions are approaching, and on one side, the solutions are moving away. This is a semi-stable equilibrium point. In GeoGebra, we are looking now at 4 solutions of dy dx is y squared minus y cubed. We found y equals 1 was stable, and you can see as I vary these solutions, all solutions nearby y equals 1 are approaching y equals 1, but y equals 0 was semi-stable. So some solutions approach, namely if I move all these solutions underneath y equals 0, they are approaching y equals 0. But on the other hand, if we start nearby but above y equals 0, these solutions are moving away. In fact, they are approaching y equals 1. And here is the picture we were just looking at. Here is y equals 1, equilibrium point, and here is y equals 0, equilibrium point. Very nice. Our third example is here, all equilibrium points of the differential equation. Now, we will write down, determine the stability, but I have a slightly different question. If you have a solution and y of 1 is 2, what is the limit as y goes to infinity, y of x? Well, maybe the first step is to try to do some factoring here so I can set capital F of y to 0. So how can I do this? Well, I can do this. We have ln y appears in this term and this term. So I will have ln times y minus 1. And then I have minus y plus 1, which I can write as this, minus y minus 1. Now see if that's correct. Check. This part we discussed. Now distribute the minus sign. We get minus y plus 1. One more step. This is factor out the y minus 1. And then ln y minus 1. Now this is wonderful because I have this factored. So capital F of y equals 0. This happens when y equals 1 or when ln y equals 1. What's the y value that gives you ln y equals 1? Well, it says take e raised to this power, it equals y. So here, y equals e. These are my two equilibrium points. Now let's make our number line. We have 1, we have e. Let's see, I cannot evaluate at y equals 0. Natural log of 0 is undefined, so let's pick here a half. And then here we can pick, say, 2, and here we can pick, say, 3. 1/2 minus 1 is negative. Ln 1/2 minus 1 is negative. We get positive. At 2, 2 minus 1 is positive, but ln 2 minus 1 is negative. We get negative. And at 3, y minus 1 is positive. ln 3 minus 1, positive, positive. So my signs of the first derivative are positive, negative, positive. We have equilibrium point, equilibrium point. We have decreasing, increasing. You see, y equals e is unstable. And then we would have, say, decreasing and increasing. Y equals 1, stable. Now we can answer the question. So y of 1 is 2, which is between 1 and e. What will happen as x grows without bound? Well, it will come to y equals 1. So if y of 1 equals 2, the limit as x goes to infinity, y of x equals 1. GeoGebra again. Well, here we are looking at 4 solutions to dy dx is y minus 1 times ln y minus 1. We first had to factor to get the right-hand side of the differential equation of this form. Okay, so you see we had y equals e and y equals 1 for our equilibrium solutions. And e is about 2.7 or so. Irrational, but that is close to that. And you see, we have these 2 different solutions, or I can make more of them, close to y equals e, and they are all moving away from the equilibrium point y equals e. On the other hand, if we get nearby y equals 1, this was our stable equilibrium point. The solutions are approaching y equals 1. We have this other part of this question. It said, suppose y of 1 is 2. Okay, let's do it. Y of 1 is 2. This is solution curve A. In fact, I will take away all of the others. The question was, what is the limit as x approaches infinity of y of x? And you can see this here. We get 1, but it really came to the fact that this y equals 1 was a stable equilibrium point. And here is this picture we just looked at. So we have approximately equilibrium point and equilibrium point like this. For our last topic example, I want to introduce the logistic growth model. If you recall, an explicit solution to the exponential growth model is here. A0 is the initial amount, And then we have e to the kt. Here k is positive if we have exponential growth. If you take a limit as t goes to infinity of something like this, you get infinity, meaning this exponential growth model, well, the population or whatever you're modeling grows without bound. Now, this is great for, say, one-time deposit into a bank account and interest. But often, population growth cannot be unbounded. It's limited by environmental factors. So this other model, logistic growth model, a population has some maximum size, capital N. It's called the carrying capacity. And the rate of change satisfies this logistic equation. We have some constant k. We have 1 minus y over n times y. So let's just look at this for a moment. When y is small, very small, think close to 0. So your population is very, very small. Well, in this case, this 1 minus y over n is approximately 1. This y is very small. And then dy dt is approximately ky. So this is the exponential growth picture. So this would be exponential growth. When y is very small, the population grows in an exponential way. Close to. But when y is close to the maximum value, well, you see this 1 minus y over n, y is very, very close to capital N. So this is very close to 0. And the rate of change of y with respect to t is very close to, well, 0. So this is what you can think about this growth model. Initially, for a very small population, we see something that looks like exponential growth, but then it starts to slow down as you get close to this carrying capacity. My note is an important one, finding a solution. So this is a separable differential equation. In order to solve this, we need to use a technique of integration called partial fractions, which you will learn in Calculus 2. And that is not this course. So that is not my goal. What I want to do is look at this qualitatively. So let's find all equilibrium points and determine their stability. Well, you see it's already factored. So the equilibrium points are y equals 0. And we can solve this one. 1 minus y over capital N is 0. This would say y equals n. So my equilibrium points are 0 and the carrying capacity n. Now let's determine their stability. So throughout this, let's assume that, it's written that k is positive. Let's draw our number line. We have 0. We have capital N. We can pick, say, -1. We can pick, say, n over 2. And way up here, let's say 2n. -1, which may not make sense as an amount of a population, but let's see what happens. So k is positive, capital N is positive. We have 1 really plus 1 over n, so that's positive. And then y is negative. Here we have negative. At n over 2, we have 1 minus half. That's positive. And then we have n over 2 is positive. This is positive. Finally, at 2n, we have 1 minus 2, which is negative. And 2n is positive, so this is negative. We have equilibrium, equilibrium, decreasing, increasing, increasing, decreasing. So what do you see? You see that y equals n. This is stable. And maybe I will move this over here. Y equals 0 is unstable. Here is just one example of a logistic equation. Here I have the K as 1/2, and the capital N, which was our maximum population size, I have this as 12. You can see these curves, they all start off looking like exponential growth. This would be for our small values of y. And then as you get closer and closer to the maximum value of 12, the carrying capacity, the growth slows down. In this graph, maybe I will just write this here. The K we can see is 1/2 and capital N is 12. You see that here, this 1/2 and the 12. So equilibrium, equilibrium. Now, I actually have one more thing to say really about this logistic equation. It's quite beautiful. So it comes in the form of a question about really any autonomous differential equation. If you have, say, dy dt is capital F of y, what is the second derivative? D squared y over dt squared. Well, to answer this, generally the second derivative, you differentiate the first derivative, and the first derivative is just here, but y is a function of t or x, whatever it happens to be. I will do it with respect to t. So it would say that d squared y over dt squared. Okay, we differentiate the first derivative, remembering the chain rule. Take the derivative of the outside, evaluate it at the inside, and then times the derivative of the inside function. Well, let me multiply this out to help me. Maybe I'll still leave this k out in front, and then I have y minus y squared over capital N. Now I can really just use power rule. So the second derivative, d squared y over dt squared, I can write down the constant. Now, differentiate. We have 1 minus 2 over n y times the derivative of the inside function, so times y prime, or dy dt. You see, what I want to look at is this part. Okay, k is a constant and it's positive. And so let's look at this part. You notice that y double prime equals 0 when here, 1 minus 2 over n, y equals 0. And this happens when y equals n over 2. So this is half the maximum amount, or half the carrying capacity. We see the second derivative is 0. Well, what else can we say here? So we could make a little number line where here is half the carrying capacity, but my number line is not for the first derivative, it is for the second derivative. So if we go slightly below n over 2, you see this positive, this positive, positive. We have 3 positives, so plus, 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 positive. If we go slightly above n over 2, positive, positive, but this one, negative. So we have positive, negative, positive, negative. What is this saying? Well, we have an inflection point at y equals capital N over 2. And this is, I think this is super cool. We can see it here in the graph. So here, capital N is 12. Here is 6 and 6, that's halfway. You see concave up, concave down. You see concave up, concave down. And this one, I don't have that point marked, but also at y equals 6, concave down, concave up. This one starts above y equals 6, so it is always concave down. But I like thinking about this in the picture. It takes us back to earlier in the semester, Calculus 1, concavity, how wonderful. So this is all I have to say in this autonomous differential equations lesson. Thank you so much, students.